Hello, everyone. Okay. Hello, everyone. Today, I'm going to present to you my paper entitled "The Fast CU Partition Algorithm for the VVenC Encoder in Intra Configuration." First of all, my presentation is organized as follows. I will start by an introduction, then the motivation to our proposed method, our experimental results, and a conclusion. So, with the emergence of video services such as video on demand, web TV, and websites of streaming, video is all the time around us in our lives. Moreover, the emerging formats of video, like the ultra high definition, the 4K and 8K, increased the video content on the internet traffic, which is confirmed by a recent study was conducted by Cisco, where they presented the global internet traffic by application category, and the global internet traffic for video traffic by resolution category. In the first figure, we can see that video represented in 2017 around 55% of the global internet traffic, and keep increasing over the years until 2022, where it reached around 71%. The same for the emerging formats like the ultra high definition, where we can see that in 2017 it represented about 3%, and still increasing until it reached 20% this year. This massive increase requires a new video coding and compression standard more efficient than the actual ones. So far, in 2020, the GV team introduced the versatile video coding standard that provides new coding tools, such as the increased mode in Intra prediction block and more new tools. The introduction of the new quad-tree with nested multi-type tree structure for the partitioning block, and the multi-transform selection, and the low-frequency non-separable transform for the transform block. In fact, these new coding features allow to VVC to provide a great coding efficiency by saving around 40% of bitrate over the HEVC, but at the cost of an increased complexity. In the random access configuration, by a factor of 8, in the intra configuration, in the all intra configuration by a factor of 25. This massive increase caused by these new features. So many researchers in the field of image processing and video coding work further to reduce this complexity. Here we can see a study was conducted by Alexander TC, where authors show that the VVC blocks offer great potential to reduce the complexity for this VVC encoder. As we can see here, for the multi-transform selection block, it provides around 55% in complexity reduction as a complexity reduction opportunity, followed by the intra prediction block by 65%, and the partitioning block by over 97%. So we focused on this last one. It is the partitioning block in VVC. And here we can see the first frame of the basketball video sequence in the common test condition sequences. It was encoded by the VVenC encoder with the slower preset in the all intra configuration and the quantization parameter of 37. In the green square, we can see a smooth area where the encoder does not do more splits for each coding unit, unlike the RAID one, where which represented a textured area, and we can see clearly that the encoder does more splits and splits further these coding units. But the problem here is how to select the optimal split for each coding unit. To do so, the encoder tests all these possible splits. The no split and the other possible split of the quad-tree with nested multi-type tree scheme of the VVC by using an exhaustive search process called rate distortion optimization process, which presents a huge search space and a consuming time process. So we aim here to directly predict the best split mode for each coding unit without passing by this rate distortion optimization process. And here comes our proposed method based on machine learning to reduce the complexity of the partitioning block in VVC. The main steps of our proposed method is first the definition of our objective, which is the classification of the six possible classes, the dataset creation, the preparation of this dataset, and the modeling and training, the evaluation of this model, and finally the implementation in the VVenC encoder. The classification is the classification of the six possible classes, which are the no split, the quad-tree split, the binary tree horizontal split, and the binary tree vertical split, the ternary tree horizontal split, and the ternary vertical split. To do so, we need to extract the features of each coding unit. By selecting the coding unit, then the calculation of its features. These features will be processed by our LightGBM classifiers to predict the best split mode for this coding unit. In the step of making our decision, here we can see that instead of using the default thresholds of 0.5 to select either the class A or the class B, we use the concept of the risk interval, which is a concept that comes to tackle the problem of misclassification, might be caused by a false prediction caused by a classifier. Here, instead of to select either the class A or the class B, we defined predefined values of each classifier for this risk interval. So if the probability value is greater than the delta max, we select the class A. If it's this value is lower than the delta mean, we select the class B. If it's in the risk interval, which is both classes. And this risk interval allow us to improve our performance, our classification performance. Then in the step of dataset creation, due to the lack of a public dataset providing encoded video sequences with their corresponding coding units, split modes, and since we work on the encoding with the all Intra configuration, no temporal relationships between frames are required. So we concatenate different images from different databases according to their resolutions, as shown in this table. These different sequences were encoded with the VVenC encoder to extract their features. The calculated features are the horizontal gradient, the vertical gradient, the mean of pixels, the variance of pixels, the quantization parameter, and the subuse complexity difference. These features were calculated on different parts of each coding unit. For a square coding unit, we calculate these features on the whole coding unit, on the two parts vertically, on the two parts horizontally, on the three parts vertically, on the three parts horizontally, and the four parts of this coding unit. The same for rectangular coding unit, except the four parts. And here we can see the flow chart of our proposed algorithm, where instead of using a multi-classifier, we used 5 binary classifiers to improve the classification performance. The first one is for the split or no split selection. The second one is for the quad-tree or multi-type tree selection. The third one is for horizontal or vertical split selection. The fourth one is for binary or ternary horizontal split selection. And the last one is for binary or ternary vertical split mode selection. So to evaluate this method, we implement it on the VVenC encoder, which is an optimized implementation of the VVC that provides all VTM's performances, and it provides 5 different predefined presets with different quality speed trade-offs that are the slow, medium, fast, and faster. We use the slower preset to evaluate this algorithm in the all Intra configuration mode over the 26 classes, the 26 video sequences in the common test condition over the 4 values of quantization parameter. And to evaluate it, we use the matrix of BDBR and the encoding time reduction. And here in this table, we can see our experimental results over the 6 classes, where we can see that our proposed method can achieve around 27% in encoding time reduction with an BDBR loss of 0.37, which is a good trade-off. As we can see here in this rich distortion curve of the four people sequence, where we can see that the original and the proposed method, the curves of original and the proposed method are very close to each other. To further evaluate this method, we compare it with the other predefined presets, the slow, medium, fast, and faster. And as we can see here, our proposed method is under the curve, which confirms that we have a gain in encoding time with a negligible increase in the BDBR. As a conclusion, our LightGBM classifiers analyze the texture inside each coding unit to predict the best and the most probable split mode over the 6 possible modes in the quad-tree with nested multi-type tree. And we could achieve the good trade-off compared to the other VVenC presets, predefined presets. And as a future works, we aim to improve our LightGBM classifiers performances, optimize the thresholds of our risk intervals, and investigate more coding unit sizes. Thank you for your listening, and welcome to your questions.
Do you have any question?
I might have missed that, but how did you choose the delta value for your threshold for the risk interval? Sorry.
Okay, thanks for your question. Actually we used these values based on experimental results that we test different risk interval for each classifier, and we found that the best risk intervals for each classifier are these values.
Okay, so that's it, experimentally, because that provide an additional trade-off between the your quality and your performance, I guess.
Yes,
Differently, okay.
yes, because it allows us to improve the classification performance by testing the both classes. If we have a value of probability between the two values of the risk intervals.
Okay, thanks.
Thank you.
Do we have another question? I actually had a follow-up question to the one that was asked. Sorry, we'll change the mic. This is better. Yeah. So the delta that you have chosen, it is the same to discriminate all classes, or do you have a specific delta between different pairs of classes?
We have different values for each classifiers, as we can see here in this table. Yes. For the three first classifiers,
Okay,
we
sorry.
have different values for.
Sorry, I missed that.
Yes, thank you.